Hello out there, high water viewers. Welcome back to another episode. Today we're going to try things a little differently, or at least something we haven't done for quite a long time, where instead of just going straight to the chalkboard like we used to, we're going to be working with prepared slides and annotating them as we go. So let me know if this is something that you prefer. I think we're going to start doing this more often. We're going to try to stick to shorter videos and see if more focused approach might be more appealing to people. So today we're going to be talking about the rational method, which is a subject within hydrology that engineers use to calculate peak flow rates for a watershed. And this is pretty popular. It's very simple. It's quite accurate. And really you only need a little bit of information. You need, of course, your characteristic land use. So this tends to be things like residential area, light industrial, woodland, there's a whole bunch of different ones. And they all have different, what are essentially like ratios of how much runoff is produced for a given amount of rainfall. So maybe it produces like 60%. That's not exactly what it means, but it's relatively rough explanation of what that is. And there's different tables where that can be looked up. Another important part of information is going to be your rainfall intensity. Now it's important to keep note that this is rainfall intensity, so this is going to be like inches per hour. It's not your total depth. So if you think about like a 6-inch rain event, obviously is going to have a very different peak flow rate if that 6 inches happens in 30 minutes compared to 36 hours, right? And we're not looking at total flow volumes or flow rate over time. That's not something that the rational method is capable of calculating. It only does peak flow rate, so we need to know what the rainfall intensity is. And if we're looking at rainfall intensity over time, then we need to look at basically the peak rainfall intensity, particularly peak rainfall intensity happening after the time of concentration. We'll talk a little bit about that as we go on. And then of course your watershed area, which is going to contribute a larger volumetric flow rate over time depending on its area. So this method's been around a long time. It's very simple and accurate to use, as we mentioned, and it works pretty well for watersheds up to 200 acres. Once you get beyond that, you're probably going to want to start looking at different methods because of infiltration rates and very long time of concentrations might start to decrease the accuracy here. And there's no series data. You're not going to be able to prepare hydrographs using this. But it's great for culvert design, storm sewers, sometimes facility design like bioretention facilities. And I pulled some of this information. It's available from a number of sources. Some of this information was pulled from the Washington Department of Transportation. I think they call it the Hydrology Manual, published in 2019. So it's recent and it's really quite good if you want to follow up on some more information there. Okay, so the rational method, let's break it down. The peak flow rate, in this case, you can use different units as long as they're consistent. It's very common, at least in the US, to use cubic feet per second or acre feet per hour, something like that. Your runoff coefficient is dimensionless, so I clipped this little bit of a table here, a really old one, I think it's from '88, from the National Resource Conservation Service. And so you can see there's a lot of different ranges for different land uses. They can really get quite specific with different slopes. Of course, higher slope is going to produce more runoff, right? Because it has less chance to infiltrate. It's going to be moving at higher velocity. And in general, more pervious areas are going to have less runoff because it's going to infiltrate. It's more pervious, right? And something like a parking lot, paved area, or a roof is going to generate more runoff because, it's impervious, right? So it's going to produce runoff very quickly and tend to have a lot of volume. And you can see that from like heavy industrial areas and urban areas having a larger runoff coefficient. And these ranges, typically you might pick a middle of the ground, average range there between, like, say, for industrial, let's see if I can, light light industrial area, 0.5 to 0.8. You might pick, right in the middle there. Unless if it's like older infrastructure, you might have less runoff because maybe the concrete's more cracked, the materials become more rough. It's going to maybe become more pervious over time. Or if the opposite, if it's very new, or maybe if it includes green infrastructure. But also if you have larger storm event, like less frequent larger storm events, like a 100-year storm event, because when you get very large storm events like that, they tend to produce much higher runoff because they're very less impacted by things like infiltration. There's the amount of runoff happening is just so much that there's really no opportunity for it to be infiltrated. So rainfall intensity we talked about. We'll talk a little bit more about that, and then watershed area is pretty self-explanatory for the most part. But the thing is, most watersheds are not one type of land use, right? So it can get a little bit complicated, and we're going to look at that in this example. We're only going to do one example today, and wow, we're already at 6 minutes, so I'm going to try to move things along. So in this case, we're going to look at a 150-acre watershed, and we have these characteristics of the watershed in this table here. So we have 3 different land uses that we're looking at, and the coverage for that land use throughout the watershed, how much of it is residential, how much is industrial or woodland. And then I went ahead and picked the coefficient for you that I'll be using if you want to use the same coefficient, or if you want to look them up in a table. Note that woodland's not in that table because that was an urban table, but there are rural tables as well. And then next to that, we have something called frequency, intensity, duration, storm curve. And this is where we compare storm duration to rainfall intensity and then the return period or frequency. So this is where we're talking about like a 2-year, 5-year, 100-year storm event, which just in very brief description means the largest storm event likely to be seen in that period of time. It's more to it, of course, but that's a pretty quick description. So we're going to look at, for this example, a 30-minute duration, 5-year storm, and then so we'll be using that information, and then we'll be neglecting the time of concentration. Now, why did I throw that in there? Time of concentration has to do, again, very brief description that's not really doing it justice, but it has to do with the maximum or the amount of time it takes for the entire watershed to contribute to a drainage area. So, for example, can I draw? Let's find out. So if we have this watershed and, it's going to start collecting water as it runs off, basically, once this entire watershed is discharging from its discharge point, then that's the time of concentration. So at whatever, for any particular droplet of water, at some point, whatever the longest amount of time it takes to get out of the watershed, that's time of concentration. And the reason we care about that is because when you have variable rain frequency or variable rain intensities, we want to make sure we pick one after that time of concentration, because that time of concentration is when you would expect it to be the highest peak flow rate. So we're going to pick an intensity after that. Okay, in this case we're neglecting it though, but I wanted to include that description just in case it comes up on like maybe a problem someone's doing or in conversation. I didn't want people to get tripped up or caught off guard. That's all you need to solve this problem. But if you're a little bit unsure, I can throw in a hint for you. But if you're feeling confident and you think you can take it on, I recommend pausing the video, giving it a shot. Certainly practice is the best way to learn and get better. So go for it. I'll see you when you get back. If you need a little bit of a hint, I will say that the biggest part here is how to handle this multiple land use and coverage. Obviously mathematically there's different ways of doing that, but the easiest way, and the way that most people are going to do it, and you'll see it done in textbooks or whatever, is to do a weighted average of your coefficient. That's going to get you done quickest and easiest. So if that helps, if you think you got it now, give it a shot. I'll see you when you get back. Okay, welcome back. Hope that went well. So let's get started on this. All right. So what was mentioned, you're going to want to do a weighted average. So the easiest way to do that, or really the way to do that, is to multiply your area so we have 150 total, right? Can I write on this? 150 AC for our total watershed. So, 0.4 times 150, 60, blah, blah, blah. We get our areas that way for these different land uses that don't necessarily have to be, total areas. They could be spread up in little chunks all over the watershed, but they add up to 40, 30, and 30%. Okay, so 60 acres, 0.5 coefficient. Let's start writing some of this out. Whoa, don't start messing up. Okay, 45 acres. And then, of course, the sum of your areas is only going to be your total watershed area. So from that, our C average is 0.485, which is just the weighted average. And so that's really all. Oh, well, we need the intensity, right? So that's just going to come off of this. We said 30 minutes. I picked 5. Maybe that was, you got maybe a little bit different number there. I went ahead and went with 5. So we have our dimensionless coefficient times 5 inch per hour times 15, what am I saying, 150 acres. And then converting that, because that's in inches, we want to get to feet. Okay. Oh. Whoops. I kind of messed up there, didn't I? Because that's not what I wanted. Wow, sorry about that. I don't know why I did that. So this is what I meant to do. Right, I meant to put this over here. So our peak flow rate is going to be our average C value times 5 inch per hour times 150 AC, and then convert it to feet, which will give us 30.3 acre feet per hour. So that's maybe a little bit of a weird unit if you're not used to that. What that means, kind of conceptually here, is if we had something like that. Say if this is 30 acres of an area here, and this is 1 foot tall, then this whole volume would be 30 acre feet. So that's just another way of handling or writing, expressing very large volumes instead of doing, millions of cubic feet an hour or something like that. Okay, that's all we have for today. How do we do on time? Well, kind of failed, about 15 minutes. Sorry about that. But hopefully this was useful, and I hope it was, maybe people like this format a little better, so let me know if you do. Either way, thank you so much for watching, if you stuck through for this long, and definitely thank you so much to everyone who has left a comment or liked our videos or, subscribed to the channel. We really do appreciate it. Thank you, and we'll see you next time.